Welcome to another video. In this video, we're going to talk about something called simple harmonic motion. We're taking a sidestep away from triangles and going back to the functions sine and cosine, really what their graphs are. So we'll talk about what simple harmonic motion is. I'll tell you how to create a function from information and how to get information about this harmonic motion from a function, and that's pretty much about it. I will not be talking about damped harmonic motion. We really haven't talked about e to a negative exponent in a while. That would be involved. So I want to get you rolling on what simple harmonic motion is in this video. So what does it mean? Simple harmonic motion is vibratory motion that does not lessen over time. So you start a process and it continues going up and down or back and forth forever without lessening. Now, oftentimes damped harmonic motion is a little more realistic, where you let something go and it does this and then eventually gets to its resting position. This would be the case where you do this and it keeps on going forever and ever and ever. What I'd like you to know about simple harmonic motion is that it can be modeled with what are called sinusoidal functions, either the sine or the cosine functions, without manipulating them or without multiplying by some other function and bounding them with an upper and a lower curve. So simple harmonic motion doesn't change over time, and it can be modeled with sine or cosine functions. So let's talk about what these things are that I've written on the board. This letter D stands for displacement, or the amount of distance between its resting position and where it is at over a period of time. Now, there's two functions we can deal with that do this, cosine and sine. And we're familiar with them pretty much, that, hey, that omega affects the period. That t is time, so over a length of time, what this is doing, where it's at over a length of time. And omega, it relates to our period. So when we deal with this, d is displacement from rest. The absolute value of A is our amplitude, how far it gets in total away from your resting position. This is usually where you push it to, pull it to, or where you hit it to from rest. The period, why is it 2 pi? Why is it 2 pi over omega? Oh man, hopefully you remember that sine and cosine have a natural period of 2 pi. We can divide that by whatever number is in front of our variable, and it will shrink or grow that period. And then our frequency is how many oscillations happen per time interval. It's really just the reciprocal of your period. A couple other things I want you to know before we move on. We'll get to this when we start building our functions. If you are starting from a position that is away from your rest, you will use the cosine function. If you are starting your motion at rest, you'll use the sine function. I want you to see why. This is what the sine function is, either positive sine, so A is positive, or negative sine, A is negative. So if your position is at rest when you start, use the sine, because sine starts at the origin, starts at 0, 0, starts at a resting position of you're not away from your period, your place of rest. Cosine's different. Cosine starts either positive amplitude or negative amplitude, whatever that is. So if you're starting away from your resting position, like you've pulled down something, let it go, or you've pushed up something and let it go, if your displacement, your position, is starting away from your resting position, use cosine. That's because it's modeled better as positive cosine or negative cosine. If you're starting at rest, continue with sine. So positive sine or negative sine. We'll also use this idea to say, from our functions, what's happening? Where are we starting? Is our motion going down from start or coming up from start? Going up from start or going down with start? And so we'll be able to determine that by understanding what our trig functions look like. So we're going to get right into it. Let's say that you have a sine hanging down from some sort of spring and you pull it way down. Well, actually it's only 7 inches. You pull it way down 7 inches and let it go. What's going to happen? Well, if you've pulled that down, remember, you've pulled it down and you're starting its displacement from down below where it wants to rest. What model fits that best? Does this fit it? Are you starting below where it wants to rest? No. Are you starting below where it wants to rest? No. Are you starting below where it wants to rest? Yes. So this is going to be a negative cosine function when we get done with it. So we're going to pull down this sine and then we're just going to let it go. We're just going to do this forever, theoretically, in this model, simple harmonic motion. Let's say you count it and it takes 4 seconds to return to where you let it go. So you pulled it down, Remember, it hasn't started its own natural motion until you let it go. So you did this. It hasn't started simple harmonic motion yet. You're just holding it. You're holding it, and then you let it go. At that moment, t equals 0 starts. So you go up right there. You have released this from below its resting position. It's going to want to go up. And you start counting. 1, 2, 3, 4, and it gets down to exactly where you released it. Took 4 seconds to get there. It's a really slow spring. And let's figure out if we can determine everything about this problem and build a function from it. Firstly, what's the amplitude? How far away from its resting position is this ever going to make it? Well, it's going to be 7 inches. You tip it down 7 inches and let it go. Our amplitude itself, the absolute value would be 7, but I want you to think of where you also moved this object, this sine. Did you move it up, +7? Did you pull it down, -7? In our case, we pulled this down 7 inches. That's -7. We'll also think of the period and use that to find our omega, the thing that's going to go next to one of our functions inside our variable, inside our parentheses next to our variable. So our period is 2 pi over omega. However, we know what our period is. Our period is 4 seconds. So if we read through this and say, yeah, we pulled it down 7 inches, that's -7. Your displacement is -7 when you start. And then you let it go. It takes 4 seconds to oscillate all the way up and all the way down from where you let it go. Then our period's 4 seconds. Let's set this equal to 4 seconds. In doing that, what we can do is solve for omega. So multiply both sides by omega divided by 4, or remember you can interchange these two things and simplify. We're going to get pi over 2. What about our frequency? Frequency is how many oscillations per time unit. So how many oscillations per second? Now think about this. If it takes 4 full seconds to go from where you released it back to where you released it, how many oscillations per second does it have? Well, not even 1. Actually, 1/4. Here's what happens. Your frequency is always going to be the reciprocal of your period. So if your period is 4 seconds, your frequency is 1/4 of an oscillation per second. And now we're actually ready to build our displacement formula. Our displacement is going to be modeled on where you pulled it to and what's happening when you release it. If you are starting, so you pull it down and start that position at that non-resting position, if you are pulling this away from rest and letting it go, or pushing it up away from rest and letting it go, use cosine. So we've already determined how far we're pulling it. That's -7. We've already determined that it's not starting from its resting position. It's starting away from that. Actually, it's starting from you pull it down. Use the -7. Cosine is use this when you start away from rest. So cosine. We have solved for our omega. That's pi over 2. And our time unit is t. That's our variable. That right there is exactly how this function would be modeled. So we would model this with the function -7 cosine pi over 2t. And I need it to make sense to you. I need you to understand that cosine starts away from 0. Cosine starts away from rest. So if this was hanging there, you pulled it down, you're moving it away from its rest, down 7 units. Its amplitude is 7, +7, yes, but where you moved it's -7. This would look like a negative cosine function. You pull it down, what's going to happen? What's its motion immediately? It's going to start going up. So if you see a -7 cosine, a negative something cosine, its initial motion is going to go up. Why? Because you pulled it down and you let it go. It's going to start climbing upward. It's going to reach a peak. It's going to right back to where you released it. That time period is your period. How many oscillations fit in that is your frequency. You can use your period to solve for omega, and that is the coefficient of your variable. Remember that is what has adjusted your period for you. We're just kind of going in reverse. So that's really the idea on going through this is, number one, see what's happening with it. Are you starting from rest? Use sine. Are you starting away from rest? Use cosine. Are you pushing it up? Positive cosine. Pulling it down? Negative cosine, because it fits the model. Are you shooting it up from rest? Positive sign. Are you shooting it down from rest? Negative sign. And then all we really have to do is find our omega from a period, how long it's taking you to return to your starting position. So let's go ahead, we'll start a couple more examples and go through this, but this is the idea. We're trying to really model what's happening in our physical simple harmonic motion to a mathematical model, this function of sine or cosine. Let's try another one. So let's suppose this is the case. You have this amplitude of 4, and you know that it's going to take pi over 2 seconds to return to where you, in this case, pushed up 4 feet and let go. So this is all very important information. Firstly, this is simple harmonic motion, and this is what we're going to imply with this situation, that if our amplitude is 4, we either pushed it up 4 units or pulled it down 4 units. We shot it up from rest 4 units, or we shot it down from rest 4 units. In our case, it says you push this up 4 feet and you let it go. Which model best fits that? Well, starting from rest would be a sine issue. Starting not at rest, displacement away from 0 at rest, is a cosine issue. In fact, we can look at this right here and say, if your displacement at time 0 is not equal to 0, use cosine. If your displacement is 0 at time 0, use sine. In our case, our displacement is 4 when we are at time 0. Why is that? Because you're pushing it up, holding it there, and then letting it go. When you immediately let it go, where is it at? It's at positive 4. Our displacement is 4 when we let it go. This means that your displacement is away from its resting position. You are using cosine here. So if we push this up and let it go, then our A, I know our amplitude absolute value of A is 4, but our A is also positive 4. Our period, well, our period is pi over 2. Pi over 2 seconds. But also remember that our period is equal to 2 pi over omega, which means our omega, our coefficient of our variable, is, if we reverse that, if our period is 2 pi over omega, then our omega is 2 pi over our period. Because we know our period, we can make a little substitution here. Omega is going to be 2 pi over 2. So we're just substituting, saying if period equals 2 pi over omega, then omega equals 2 pi over period. We know our period, just substitute it. In our case, our pi's are going to cancel. We're going to get 2 divided by 1/2. That's 4. Omega is just 4. If you wanted to figure out your frequency, if you were ever asked for that, because your period is pi over 2, your frequency would be 2 over pi. There would be 2 over pi oscillations per second. That's how you find frequency. It's not asked for right now, but you could find it. That'd be 2 over pi oscillations per second, so less than 1 oscillation per second. So now we're ready to figure out our displacement function. Displacement is, find your A. Now, if your amplitude's given, and you know that it's 4 in our case, you need to know whether this is pulled up or pushed down to start. This one was pushed up, so we know that this is positive 4 units away from its rest. Use that number. So this would be 4. We know that we're starting away from rest, so use cosine. We've taken some time to figure out our omega. That's a coefficient of our variable. That's 4t. And that's really it. That right there would give you the model of displacement. Now you can check your work. If you know that its displacement is 4 at time equals 0, plug in 0. 4 times 0 is 0. Cosine of 0 is 1. 4 times 1 is 4. So this actually gives me my initial position based on my starting time of 0. That's a good way to check your work. So if you had accidentally had a negative here, you plugged in 0, you get negative 4. You go, wait a minute, I know I'm at positive 4 when I start. That's a problem. What if you had chosen sine? Well, then 4 times 0 would be 0. Sine of 0 is actually 0. 0 times 4 would be 0. And you go, oh, this is starting at rest, not where I want it to. This is why we choose sine for starting at rest and cosine for starting away from rest. Because sine of 0 is 0. You have to start at rest. Cosine of 0 is 1. You have to start at your amplitude. That's why that works. So in our case, this would be you're pushing something up and letting it go. Where's its initial motion? Is it climbing or is it falling? Think about this. Positive cosine functions fall immediately. That's what would happen if you push something up and let it go. It's going to fall. If you pull something down and let it go, it's going to climb on a spring or something. So this right here, this initial motion is falling. It's going down. What if you were to pull this down and let it go? Well, then our initial position would be negative. It'd still be cosine, but it'd be negative 4 cosine 4t if you had pulled this down 4 feet or something and let it go. I hope that's making sense to you. I hope you're seeing a little bit more the modeling of cosine away from rest, the idea of if I pull it up and let it go, it's this model and it's going to go down first. If I pull it down and let it go, it's this model. It's going to go up first. Let's go ahead and try a couple more. Okay, I lied. I wanted to change something on the previous problem. Let's suppose that instead of pushing this up or pulling this down, this is at rest and it's moving up. So imagine this. Imagine you have like a ball on a string and you just hit, or a spring, I should say, and you hit it. So here's the ball, you just hit it upward. What's going to happen? It's going to start at rest. You hit it. It's immediately going to go up and then come down and go up again. So let's say that it takes pi over 2 seconds to go up and come down and go back up to hit its resting position. It's going to continue. Let's imagine that it still hits up to 4 feet up. So our amplitude is still 4 feet. Our period is still pi over 2, but it's starting at rest and moving upward. Which model now fits that? These are both not starting at rest. This is starting from a displacement away from that. These are both starting at rest, but which one starts with the motion up? Positive sine or negative sine? Well, positive sine does. Positive sine would be this case. You have the ball hanging there, you hit it, it's going to start at rest and go upward. Then it's going to come back down and go upward again. So when we're taking a look at that, we're always going to use sine for starting at rest at time 0. Because sine of 0 gives you 0, it's going to zero out that and start you from your resting position. So we still have the amplitude of 4, sure. We actually still have a positive 4 because we're dealing with a positive sine function. Our displacement, though, is 0 at time 0. We're not, at time 0, right as you hit it, its initial position is at rest. It's at 0. So our period would still be the same, our omega would still be the same, but we're using a different function. We'd use moving up, means we're having a positive sine function. We do have 4, so positive 4 though. Sine of 4t. Think about the model here. If you plug in 0, 4 times 0 is 0, sine of 0 is 0, 4 times 0 is 0. At time 0, you are at rest. Now you hit it. What's happening? It's going up. Why do we know that? It's positive, and so it would be climbing. This matches moving up. What if I would have had a negative in front? Well, if I would have had a negative, this would be a negative sine function. That's the purple one. That would say, hey, I'm going down. Oh, that's not moving up. That would be a problem. Which model would this fit? This would fit a model of you're at rest and you hit it downward. That would be initial motion down. It would be negative. It would follow that, and that would work if that word was down. I hope that makes more sense now. I hope that you're seeing the interplay between cosine away from rest. Sine starts at rest because cosine of 0 is 1, but sine of 0 is 0. It puts it at the resting position. All right, we're going to take a look at 4 functions really quickly just to get a feel for how these look based on the function. So we have a displacement function here. The displacement of this object equals 5 sine of 3t. I just want to get in your head what this would look like and what this is doing just simply by reading the function. So let's start here. Can we see what the motion is, what type of a motion is, whether we have damped harmonic motion or simple? Now, we haven't talked about damped harmonic motion, but damped would decrease with time. It would have an actual decaying exponential, e to a negative exponent. So this doesn't have that. This is going to continue oscillating over and over and over, just like sine and cosine both do. So this is simple harmonic motion. There's nothing in that that's lessening the function over time. How about the maximum displacement? This is also your amplitude. How far does this get away from its resting position? Well, that is always that number in absolute value. So that would be 5. 5 units away from its natural resting position before it started taking motion. How about the time for one oscillation? What that's asking for is the period. How long does it take to go from where you're starting it, either away from rest or at rest, back to where this whole situation started? Well, that is a period. How long does it take to create one oscillation? Our period is always 2 pi over omega, or it's the amount of time that it takes if it's given to you. So because we have that 3, our period is 2 pi over 3. Remember that we can adjust our period by dividing by the number in front of our variable. In our case, that is 3. So period's always 2 pi for sine and cosine, pi for tangent and cotangent. We don't have to worry about that here, but for sine and cosine, it's 2 pi, that's the period, divided by whatever that number is. This is shrinking that period or compressing that. So our time for one oscillation is 2 pi over 3 seconds. How about your frequency? Frequency is always the reciprocal of your period. So if we have 2 pi over 3 seconds to create a full period, it'll be 3 over 2 pi oscillations per second. How about your displacement at time 0? Like, what would you do there? You can either read the function or just plug in 0. So if you just plug in 0, 3 times 0, plug in 0 for t, that's times 0. Plug in 0 for t, 3 times 0 is 0. Sine of 0 is also 0. 5 times 0 is 0. Your displacement is 0. That means that this position is at rest when the situation starts. You could also look at the function. This is a positive sine function. Okay, well, what's a positive sine function? That's this guy right here. Positive sine functions are like this black one that goes up, comes down, goes back up. But where does it start? It starts at 0. It starts at rest. Now, this answers the next question though. What's its initial motion at time 0? When it starts, what does a positive sine function do? Does it climb? Does it go up? Does it fall? Does it go down? In our case, a positive sine function climbs, so its initial motion is upward or climbing. I hope it makes sense. I hope you can now read the function and see, like, yeah, this is not going to change over time. Its displacement is its amplitude. It's 5 away from rest. Our period's pretty easy. We've studied period before. Frequency is the reciprocal of that. Its position is at rest when this starts because its displacement is 0. And then its initial motion is modeled on whatever function that's given you. So sine functions start at rest and either move up for positive or down for negative. Cosine functions start away from rest and either move down for positive or up for negative. So let's come back with 3 more. We'll go through them very quickly, do basically the same thing. Okay, so we've got another one. We got d is -3 sine 1/2 t. Let's go ahead and answer all of these questions. Let's assume everything is in meters, like we will for the next couple examples. Firstly, do we still have simple harmonic motion? Yeah, there's nothing that says otherwise. Sine functions continue on forever and ever and ever unless we just truncate them or alter them with some other function that binds them in some way, that bounds them. How about our maximum displacement? Our maximum displacement is how far away from rest does this ever get? That absolute value of your very first coefficient, the absolute value of -3 will tell you that. That's your amplitude. Your maximum displacement would be 3. Your period, or the time for one oscillation, is always the period of your function divided by omega, the number in front of your variable. So in our case, that's 2 pi divided, oops, did some math in my head there. 2 pi divided by 1/2. If we multiply by the reciprocal, we end up getting 4 pi. So our period, the amount of time that it takes for one oscillation is 4 pi seconds. Our frequency is the reciprocal of that, so 1 over 4 pi. So it'd be 1 over 4 pi oscillations per second. What about our displacement at time 0? Just plug in 0. If I plug in 0, 1/2 times 0 is 0, sine of 0 is 0, 0 times anything including -3 is still 0. So this displacement is 0 at time 0. It is at rest when this situation starts. You can see it from the function also. If this is a negative sine function, both positive and negative sine functions start at rest. So this would tell you your displacement is 0 at time 0. And lastly, the initial motion. This is where you have to think about it. Think about what negative sine functions do. Negative sine functions go down when they start. So this is like someone hit something downward. This would be going down at the start, so its initial motion is downward, not upward. It's kind of nice for sine because positive means upward and negative means downward. Cosine's opposite though. Positive cosine functions start down at the beginning and go up for negatives at the beginning. Let's try one a little different. Let's work on a cosine function. So our displacement is -2 cosine of 2t. Is it still harmonic? Simple harmonic motion. Yeah, cosine functions do the same thing as sine functions in that they repeat forever at the same maximum amplitude. So we still have a simple harmonic case. What is the maximum displacement? That's still an amplitude question. So we look at the very first number, this number in front of cosine or sine, and we take the absolute value. The maximum distance away from rest here is 2. Now, because the period for cosine is the same as the period for sine, 2 pi, we can find the period the same exact way. Take 2 pi and divide by the number in front of your variable, that omega, that 2. So if I simplify, we're going to get pi. So it takes pi seconds for this to complete its one full oscillation. These are typically in terms of seconds. If not, you'd have a different time unit, but it would be whatever that period is time units to create one oscillation. Frequency is the reciprocal, so it'd be 1 over pi oscillations per second. How about its displacement at time 0? Two ways to do it. Either just plug in 0 and that's fine. 2 times 0 is 0. Cosine of 0 is 1. 1 times -2 is -2. This starts at -2 units or -2 meters below rest at time 0. So mathematically, displacement is -2. That means it's 2 units down. What that means verbally is this starts 2 units or 2 meters in this case, if we're using meters, below its resting position right when you start. So someone held this down and let it go. Held it down 2 meters, and let it go. Its initial motion. Well, now you could have answered this question by looking at the graph, and we could do that. So here's cosine. What would have a display? What would our negative cosine look like? A negative cosine is like the purple one. It starts down here and goes up. Would that have told you that your displacement is 2 units below rest? Yeah, 2 meters below rest. Now, how about initial motion? Think about this. If this is a negative cosine graph like we have, its initial motion would be upward. So when you pull something down and let it go, its first inclination of motion would be up, not down, up. This is where some students get confused. They think negative always means down. It doesn't with cosine. A negative graph would start climbing upward immediately. I hope it's making sense. I hope you understand the negative cosine starts upward. I hope you're seeing the differences between sine and cosine. Cosine functions start away from rest at their initial position. Last one, and then we're done. How about D? Our displacement function equals 6 plus 2 cosine pi over 2t. Oh my goodness. Is it still simple harmonic motion? Yes, because that's what cosine does. What in the world is a 6? The 6's initial starting position above 0, but it's still its resting position. It's like you're saying, hey, I'm holding this ball 6 meters above the ground. Now, from there, it's just holding there on a spring. Now hit it. What's going to happen? It's going to start at 6 meters, but then from that position, it'll climb, it'll go below, it'll come back up. But it's like resting position is not at 0. That would be like at the ground anyway. So maybe this is a little more realistic. We have this thing that's hanging 6 meters above the ground. From there, we're going to swing it back and forth. So some sort of simple harmonic motion is still simple harmonic motion. What's its maximum displacement from rest? Not 8. Why? Because 6 is its resting position. From there, it will climb 2 or go down 2, that's fine, but it's only changing 2 units, 2 meters from its resting position. So its maximum displacement from rest is still 2. That's why the amplitude has nothing to do with a vertical shift. Our amplitude is from where it is, how much does it go up and how much does it go down. It is at 6, has nothing to do with a vertical shift. That is a vertical shift. It's just the absolute value of the coefficient of your function. So it would just be absolute value 2. It's just 2. That's how much it's changing total from its rest at 6 meters. How about the time for one oscillation? It's still a period question. So our period is still 2 pi, because that's cosine, divided by pi over 2 in our case. Which would still give you 4. So this is still 4 seconds per oscillation, or the reciprocal of that is 1/4 of an oscillation per second. That's our frequency. How about our displacement at time 0? Now before we do this, this is displacement from rest, not total above the ground idea. That would be a different question. What would its total be from a height of 0? And you'd say, okay, plug in 0 and you would get 8. Pi over 2 times 0 is 0, cosine 0 is 1, 1 times 2 is 2, 2 plus 6 is 8. That would be total height. If you're going displacement from rest, then you stop here and you don't add the 6 because its rest is at 6. So displacement from rest at time 0 is 2 still. And lastly, what's its initial motion? Think about what cosine does. A positive cosine function, even if you shift up 6 units, so like 2 cosine pi over 2t plus 6 would be shifted up 6 units, it's still a positive cosine function. It still looks mostly like this. It might shift up, but its initial motion would be downward. Positive cosine functions from their starting position initially drop. They do not climb. So this would be down. I hope I've given you a good introduction into simple harmonic motion. Like I said, we're not going to be covering damped harmonic motion in this video, but for simple harmonic, I hope that now you understand the interplay between sine and cosine and the functions that you get. I hope you understand the initial motion and the displacement from this resting position and where you start up or down depending on whether you're talking about sine or cosine. So hopefully you enjoyed the video. Hope it made sense to you, and I'll see you for another video.